Hello class, welcome to our first of two lectures on polymer structures. This is a follow-on to our Chapter 3 two lectures on crystallography, which dealt mainly with the 3D periodic array that makes up most metals and ceramics. And now we're going to move into polymers, which, as we'll see, kind of has a 1D version of the same thing. So we can start with what is a polymer. It actually has a very literal definition. Poly meaning many and mer meaning repeat units. In this case, a repeat unit is typically an organic covalently bonded molecule, usually a CH group, or it could be a silicon-oxygen covalent bond. So here's an example of one for polyethylene. You can see the repeat unit in this case is a carbon-carbon bonded with hydrogens off the side. The bonds along the length joining the carbons are what's typically referred to as the molecular or polymer backbone, and then the hydrogens in this case are called side groups. Those hydrogens can be replaced with any kind of molecule you want, including another long branching chain of polyethylene, and that'll really change the properties of the molecule. For instance, if we replace one of the hydrogens in the repeat unit with a chlorine, so that's one of the four hydrogens replaced with a chlorine, we get polyvinyl chloride. And that would then repeat all the way down the chain. If we replace one of the hydrogens with a methyl group, we get polypropylene. And that's what it would look like going in both directions. Now these are fairly large molecules, so if you think of something like methanol having basically one carbon with a hydroxyl group on one side and hydrogens, and then ethanol being just two of those, C2H5OH, these are more like tens of thousands to a million repeat units, so much larger scale than your typical organic molecule. So what drives properties in polymers? So we have similar arguments to what we had with elemental composition and crystal structure for metals. So we've got a composition side and a structure side. So properties will be affected by the repeat unit chemistry itself. For instance, polyethylene and polypropylene will behave fairly similar compared to, say, PVC or even polystyrene, because that repeat unit is quite different. Molecular weight is the next biggest swing factor. Aside from repeat unit chemistry and whether something is effectively a thermoset or a thermoplastic, molecular weight is probably the single characteristic of a polymer that defines the majority of the properties. And even in the case of a thermoset versus thermoplastic, since a thermoset could be considered to have effectively infinite molecular weight, even that is a molecular weight driven property. Molecular shape. So for a given repeat unit chemistry, say polyethylene or polypropylene, a given molecular weight, the length of the chain, the number of repeat units. Is it one big long chain? Is it a chain that branches a little bit or maybe has some loops back on itself? All of that will also change properties. And then molecular structure, not so much for polyethylene, but something like PVC, where you have a different group on the side chain. Are they all on the same side? Do they alternate? Are they random? As we'll see, that has a big effect on whether or not a polymer can crystallize, which then in turn drives follow-on properties. So this gives you a little chart just showing all of the different properties of polymers and how they're affected by structure and composition. So if we kind of start down at the molecular level, at the repeat unit level, we have over on the left, on the upper left, the chemistry of the repeat unit, and this will change the polymer name. This is polystyrene, nylon, Kevlar, all of those, although Kevlar's trade name, but all of those will have a different repeat unit chemistry. Size, which is molecular weight, how long is the chain, or in the case of a network polymer thermoset, it's effectively infinite. Shape, and this has more to do, or we could call this conformation, and this will change based on processing. Are the chains kind of all elongated and pointing in one direction? Are they totally randomly oriented? Are they crystallized? Are they amorphous? You know, how are they sitting for their given size and shape? Then we go over into structure, and we can get even more choices. If you have a thermoplastic, it could be linear, all one big long chain. It could be branched. You could have a thermoplastic with linear molecules or branched molecules that are linked up at irregular intervals. This is what's done to vulcanized rubber with a sulfur bond. This is called cross-linking. Or you can effectively be cross-linked at every repeat unit, just sort of the ultimate infinite cross-linking. That's called a network polymer. And that's what you get when you react multifunctional polymers like epoxies. Then there's isomeric states, and for you chemists this will be something fairly familiar. This has to do with the geometrical and reflective symmetry of any kind of non-symmetric, non-uniform repeat unit. And so this is whether you have a cis or a trans arrangement with a repeat unit that has a single or two different radicals coming off the side of the backbone. And then the isotactic, syndiotactic, and atactic refer to the arrangement of side groups with respect to a main chain. So isotactic is all of the unique side groups on one side, syndiotactic is regularly alternating, and atactic is random, anything goes. Okay, zeroing in on polyethylene, since it's probably the simplest polymer that we can envision. What characterizes it? No polar groups. It's a very non-polar molecule, so not only is the backbone covalent, all of the side groups are covalently bonded into the backbone, and there's almost no charge separation within those bonds. So it wouldn't attract water, and it has almost no chance of dipole-dipole secondary bonds between chains. It doesn't have any bulky side groups, like a big styrene group or a benzene ring or a short side branch that would make it difficult for chains to lie close to one another. When something gets in the way, physically gets in the way of something else, when we're talking about molecular level interactions or chemical reactions, the word that refers to that is steric hindrance. And you can think about it as just hindering, getting in the way of something. And from the standpoint of polymers, what you're usually getting in the way of is some kind of secondary bond between chains wanting to lie side by side, or a chain folding over and laying back across itself, which is how polymers crystallize. So bulky side groups will prevent polymer chains from associating side by side, either with polar bonds, the way we saw with the nylon 6,6 in the secondary bond section back in chapter 2, or to make a full polymer crystal. So if you don't have polar groups, and you don't have any kind of steric hindrance considerations, for a given repeat unit chemistry, all your properties are going to basically flow from molecular weight. So let's get a look at something where polarity is important, and this is nylon. So where do we get that charge separation? Well, you can see that you have an NH group in the main chain. This is an amine group. Remember the FON bonds, the fluorine, oxygen, nitrogen, they're very electronegative atoms. They're very electron withdrawing. So if you take a look at that nitrogen-hydrogen bond, most of the electrons are going to be sitting close to the nitrogen, not near the hydrogen. So the hydrogen's pretty electropositive. It's going to have a partial positive charge on it, that little delta positive that we saw back in chapter 2. Carbonyl group, on the other hand, has an oxygen with a double bond, and compared to carbon, it's pretty electronegative. So it's gonna hold on to more than its fair share of the bonds. Even though it's a covalent bond, it's not totally equal sharing. So if you took two of these molecules and laid them side by side, the nitrogen-hydrogen bond, being electropositive, would want to kind of butt up against the carbonyl group, making a dipole-dipole secondary. And that kind of interlocking indexing, so to speak, actually allows us to crystallize very well and contributes to stronger mechanical properties, even though it's just a thermoplastic. Flip side, nothing's free, right? Because it's polar, it tends to attract water more. And the more of these polar groups you have in a polymer main chain, the more the polymer is going to tend to swell and interact with water. So if we swell, we lose dimensions, and we also tend to lose a lot of mechanical properties. We call this plastidization, when a small molecule diffuses in and is associated in the polymer matrix, gets between chains. It keeps them from entangling quite so closely and helps them slip past each other. It's called increasing free volume. We do this deliberately for processing, but usually in surface it's not something we want. So polarity is a double-edged sword. It helps us to a certain extent by improving crystallization capability and giving us some secondary bonding between chains, but you're more water sensitive. Okay, steric hindrance. Polystyrene is a classic example. We've got a big bulky phenyl group on the side. So polystyrene would be polyethylene if we replace that phenyl group with a hydrogen. It's huge, especially compared to the rest of the repeat unit. So if you envision this chain going out to both sides, almost infinitely long, from the point of view of, say, 1,000,000 repeat units, and it tries to fold over on itself or tangle itself up to give us some mechanical properties, mechanical integrity, those big phenyl groups are going to prevent the chain from folding in and entangling quite so closely. It'll prevent it from crystallizing completely unless those phenyl groups are present in a very regular pattern. So this is why polystyrene is amorphous, again, unless those phenyl groups are arranged in an isotactic or syndiotactic arrangement, which is rather expensive from a synthesis standpoint and extra charge. You can also get bulky groups in the main chain itself, and polycarbonate's an example of that same kind of phenyl group being in the middle of the chain rather than on the side. This has a little bit different effect. Because those groups are bulky and effectively stiff, it prevents the chain from being flexible. It makes that main chain stiff. This is something that you see also in Kevlar and Nomex, some of the high-strength aramid fibers. So this is going to lead to an increased modulus and strength in the molecule, provided that we can still get chain entanglement. Okay, so back to the case where, for instance, we don't have polarity, we don't have any kind of steric hindrance or steric chain stiffening. We're back to molecular weight really determining most of the properties. So for a polymer, the molecular weight is the mass of a mole of polymer chains. Okay, so if you got a short chain, you got a low molecular weight. If you've got a long chain, you have a high molecular weight. So this is totally analogous to, say, methanol having a lower molecular weight than ethanol. The big difference in the case of polymers is you can have maybe a 5% change in molecular weight, and while you will change the mechanical properties and diffusivity and viscoelastic properties, it will still effectively be the same material. Well, polyethylene with 1 molecular weight is pretty much, it's still polyethylene if you switch the molecular weight. If you change the molecular weight by 1 carbon-hydrogen group's worth going from methanol to ethanol, you have a completely different compound with very different properties, which you'll find out if you don't make beer right, correct? Ethanol is non-toxic and methanol, not so good. So polymers are different in that we can actually change the chemistry by changing the molecular weight without changing the material's base characteristics. So that is something a little bit different if you're used to working especially with small organic molecules. Adding another CH2 group does not totally change the molecule. On the other hand, if you change the number of repeat units a lot, you will change the properties. And so we need a way to describe what the average molecular weight is for a polymer sample, because as you can probably guess, all the chains are not ever exactly the same length. There is a distribution of molecular weights for any kind of synthesized and processed polymer, and it definitely drives properties. So if you've ever spec'd out polyethylene or are looking to purchase it, these are some of the acronyms for polyethylene: low density polyethylene, medium high density, and ultra high molecular weight. These do have different densities, but the descriptions mainly refer to differences in molecular weight. So as you go from the left-hand side of that acronym alphabet soup over to the right, you're going to see an increase in strength, an increase in both yield and tensile strength. You're going to see an increase in glass transition temperature, higher resistance to deformation at a given temperature and a given load. Viscoelastic properties will become stiffer effectively. Generally, chemical durability increases and permeability will also increase. So lots of changes, but the big ones being mechanical viscoelastic, which we'll talk about in detail later on. Okay, and here we go. Here's our list that I was just going through, basically. Important mechanical properties that depend on molecular weight. So we've got melting point for the crystalline portion of polymers, glass transition temperature for the amorphous portion of polymers, and that's a particular definition that we'll get to later, but it's basically refers to the temperature at which an amorphous solid goes from being a fluid, a viscous fluid, to being either a rubbery solid or a rigid solid. And it's typically very, very abrupt, somewhat akin to a ductile to brittle transition in some types of metals. Crystallinity is dependent on molecular weight. Obviously, if it's too small or if it's over too broad of a range, the smaller molecular weight components can actually inhibit crystallization of the larger ones. Obviously, strength, thermoplastic, where you just have long chains, you don't have any cross-linking or network formation. The more chains can entangle, the stronger the material. In fact, that is the only mechanism by which we get strength in polymers if we don't have any secondary or primary cross-linking bonds. Stiffness, although to a lesser extent, and then viscosity. And for polymers, viscosity is effectively a mechanical property similar to yield. It's one of the viscoelastic properties. So if you look at molecular weight as a distribution in our graph over here to the right, this is effectively a histogram of the number of molecules in a given polymer sample versus molecular weight. So way over to the small end, obviously there's a cutoff. 0 molecular weight, there wouldn't be any molecules because there wouldn't be any polymer if it had 0 molecular weight. Ramping up fairly steeply because this is a high average molecular weight material, especially compared to liquid organics, for instance. You get to a point where there's a maximum. So there is some molecular weight for which the majority of the molecules have that particular weight. And then as you go to higher and higher weights, there's fewer and fewer of the number of molecules, the chains in that sample that are going to have those really big weights. And getting way out to the end, maybe you've only got 1 or 2 of these huge, really long ones. These distributions can be narrow or broad. This depends on how they're synthesized and to a lesser extent how they're processed. The properties of the polymer will depend on both the height of this distribution, or in its position in molecular weight, and its width. So in terms of the average molecular weight, we'll be looking at different ways to calculate the position of that peak that you see on the graph. But it's also important to understand how wide the distribution is, because if it's very, very wide, even if the average is the same, the properties will be very different. So we're going to go over a couple of ways to calculate important parts of the molecular weight distribution, and by learning how to do both of them, we will have a way to assess both the average molecular weight, which is the molecular weight of at or near the peak on the distribution, and then how wide the distribution is. So these are called the number and weight average molecular weights, and they are basically 2 different weighted averages for the distribution. Really simple concept with a couple of different definitions that can get confusing. So feel free to look back at the definitions as you go through to do any of your calculations. So in this case you have M sub n with the bar, meaning number average molecular weight, and it is the sum of the number fraction of chains of any given size or size range times the molecular weight of that size range. So if we had 10 polymer chains in our sample, any one polymer chain with any given size, its number fraction would be 0.1. It's 1/10 of the total number of chains in the sample. So if we had 10 chains and they ranged in size evenly from 10,000 to 100,000, give or take, we would just sum 0.1 times 10,000, 0.1 times 20,000, etc., sum them all up, and we would have the number average molecular weight. The weight average molecular weight, m sub w with an over bar, is the same as the number average, but instead of using the number fraction, we use the weight fraction of chains in the size range I. So in that case, we have our 10 chains with their weights in a range from, say, 10,000 to 100,000. We would add up the total weight. So 10,000 plus 20,000 plus 30,000, blah, blah, blah. Get up to that number, and the weight fraction of, say, the smallest chains would be 10,000 over that sum of weight. So it's the amount to which that size of chain contributes to the total weight rather than to the total number of chains. And then m sub I in this case would be that 10,000, whatever our unit is, usually grams per mole. When you look at the distribution of the molecular weight distribution plot with amount of polymer on the y-axis and molecular weight on the x-axis increasing from left to right, the number average molecular weight is by definition always smaller than the weight average. Always. Regardless. And it's because the distribution isn't symmetric and because of the way it's calculated. Because they're always offset, if we look at the ratio between the two of them, this gives us an estimate of the width or the range, the breadth of our distribution. So if the number and weight average molecular weights were almost right on top of one another, we'd have a very tight, narrow distribution. And if they were very, very different, m sub n was much, much less than m sub w, we'd have a broad distribution. So we're going to step really quickly through a molecular weight calculation example based on number of students in a class and their body mass, just to get an example of the calculation. And for example problems and homeworks, there'll be a lot more opportunity to give this a try. So this is just the first one. Don't necessarily expect to get out on the first go, but again, it's just a weighted average. So if you had 10 students in a class and they each have a different mass, we can calculate a number and a weight average weight for the class. So first step, we sort everybody into weight ranges. So we'll use 40 pounds as a range and we'll restructure the table. So we're going to look at the number of students that fall into these low to high mass ranges. So we got our lightweights there in the 81 to 120 mass range. There's 2 students, so number of students per range in that range, n sub I is 2. The next range up we got 2. The next range up we got 3. So n sub I is indexing per range, and if you add up n sub I over all the ranges, of course you better get the same number of students that was in the class, so that's 10, so that works. Then we have the weight total, the mean weight of all of the students in that range. So we have 2 students in the 81 to 120 pound range. So if we go back and look at who those were, that looked like it was student number 1 and student number 2. So 104 and 116. If you take the mean of those two students, you get 110. And that's what we see here. So W sub I is the average for N sub I within each range. And again, if you add those up across all of the students, you should end up with the total weight in the class. So we see 1,881. You can add it up on your own at your leisure. This is similar to the idea of the mean value theorem in calculus and some of the numerical techniques where we look at an average across a small range, add it up, or squeeze it down. And this is the foundation of a lot of our molecular weight analysis methods like size exclusion chromatography. So there's the total number of students and again the total weight. So the weight of the whole class is all of the WIs added up times the number of students in each interval. So we'll calculate the number and weight fractions of student in each weight range. So if you take the number of students in a given 40-pound range and divide it by the total number of students, which is the number in each range across all ranges, you get the number average x sub I. If you take the number of students in a given weight range, so each one of those 40-pound ranges, times the average weight for that range, so range number 1 is 110, range number 3 is 184, for instance. So n sub I, or n sub 3, w sub 3 would be 3 times 184, for instance, and then divide that by the total number of students, the total number of per range weights, sum it all up. That gives you the weight fraction for that range. And there's the example of x sub 1, the first range, being 0.2, and then w sub 1, being 0.117. So this is all of those numbers added to the table. Now all we have to do is sum them up. So the number average molecular weight, or class weight for these students, is simply x sub I times m sub I for each one of those ranges. And so for the most part, your x sub I, then the number fraction of students within each range, is pretty much the same. So you have 0.2, 0.2, 0.3, 0.2, and then 0.1 at the end. And multiplying that by the average, the mean weight for that range, we get 188 pounds. Not too bad. Good fit class, I guess. Now if we do it for the weight average, we again are multiplying that same WI, the average weight for each range, but then we're instead of x sub I, we have w sub I. And that's a little bit different, and as you can see, we get a higher number. So this is what we just gone over with the weight average being higher than the number average. Another kind of a mental example for number versus weight average is to imagine an elephant and a flea. If you combined their weights to say 1,000 pounds, if you took the number average weight of the elephant flea combination, you would say they are each on the average 500 pounds. That's obviously not very accurate, and the weight average would be something more like the elephant is pretty much 1,000 pounds and the flea is insignificant. So if you're ever wondering about a mental image of number versus weight average, you can think of the elephant and the flea. Okay, another way to look at just the formulas for number and weight average molecular weight, and this leads to more terminology that you might see in literature. Another way of writing the formula for number average molecular weight is the sum of the number of molecules in any given interval, each one of those little ranges, times the molecular weight of the range over the sum of the numbers. If we write the weight average molecular weight formula using the same conventions, we end up with the sum of n sub I times m sub I squared over the denominator. So if you take that squared term in the numerator and an index to that, you get what's called the first or second moment of the molecular weight distribution. It's just a mathematical term. And so it's another way of expressing number and weight average molecular weight. If you continue this on using other weighted averages. You can get the third moment. You can also get more empirical definitions, such as the viscosity average molecular weight, which is between number and weight average and has to do with a larger molecular weight polymer when it's dissolved, basically having a higher hydrodynamic resistance. And that's another way of actually measuring molecular weight. There's a special term for the ratio of weight to number average molecular weight, and that's called polydispersity index. And again, the important thing about that is it's a measure of the breadth, the width of the distribution. Okay, degree of polymerization is more of a synthesis-specific description of molecular weight, so it's the average number of repeat units per chain. So here we have polyethylene again with the repeat unit shown over in parentheses, kind of on the left-hand side of the chain, second one in. So we have 6 of those in this particular chain, so the degree of polymerization would be 6.